Hello everyone, I welcome you all to this session. In today's session, we'll discuss about Module 4. So in that, we'll discuss feedback amplifiers. Now, basically, the amplifiers are used to increase the strength of the signal. And the weak signal is applied to the amplifier block and we'll expect a large signal. To improve the performance of an amplifier, we'll use a feedback. By using a feedback, some of the parameters of the amplifiers can be improved. The meaning of feedback means a part of output is fed back to the input. The output will be given back to the input. That is called as a feedback. And here we'll discuss about the introduction to the feedback amplifiers. Discuss about the block diagram of feedback amplifiers. Then properties of feedback amplifiers, advantages of feedback amplifiers, then types of feedback amplifiers. So in that we'll discuss about voltage series feedback amplifiers. So introduction here, the purpose of the amplifier is to amplify the input signal without changing its characteristics except its amplitude. So a weak signal is given in terms of millivolt and all, small signal, and the output side you can expect the amplitude in terms of volt. So there is an increase in the strength of the signal. The amplifier that works on the principle of feedback is called as feedback amplifiers. And here the feedback is a process where the fraction of the output, either voltage or current, is fed back to the input. As I mentioned, the part of the output is given to the input, either in terms of voltage or current. The process is called as a feedback. A simple block diagram of a feedback amplifier is shown in the figure. So here, this is an amplifier block, and this is your feedback network. And this is my input signal, Vin. And this is Vi that is given to the amplifier, and this is V0, we'll call it as an output signal. And here one more block is mentioned. This is called as a mixer. Here the input signal and the feedback signals are mixed. Basically there are two types of feedbacks are there. One is negative feedback, other one is positive feedback. The negative feedback concepts are used in amplifiers, whereas positive feedback concepts are used in oscillator circuits. The difference between negative feedback and positive feedback is here the input signal and the feedback signals are out of phase. So there will be a difference between input voltage and either input signal or feedback signal. It is called as a negative feedback. Whereas in a positive feedback, input and feedback signals are in phase. So it will be added. That signal will be added by using this mixer block. Here this A indicates the amplifier gain without feedback. So the output will be V0 by Vi. The gain A is given by V0 by Vi. And with feedback, we will include this feedback network. And this feedback network is generally made up of passive components. Passive components like resistors, capacitors, inductors, and here you can observe part of output, that is V0, is given as an input for the feedback network, and the Vf is the feedback signal. So this is your block representation of feedback amplifiers. Now, what is the properties of feedback amplifiers? Why? What is the advantage and the properties of feedback? Why the feedback is required? So properties of negative feedback amplifiers are desensitize the gain. Means the gain will be less sensitive to the variation of any other parameters of a feedback amplifier circuits. Like is there any temperature changes, it will be desensitized, and if there is any changes with respect to the circuit component and all, it will be desensitized. So the gain will be desensitized. So generally in negative feedback amplifiers, the gain will be reduced but it will be stabilized. You'll get a stable gain. And the second property is it reduces the nonlinear distortion. So without feedback, there will be distortion. The distortion will be reduced. The distortion is mainly due to the circuit components. I'm using many components like active components and passive components, and due to that there will be a chance of distortion. And if I use a feedback, the distortion will be reduced. The third property is reduce the effect of noise. You know that the noise is unwanted signal. In an amplifiers, this noise will be added due to temperature variation or due to your circuit components and all. And if I use a feedback, the noise will be reduced. Then fourth property is control the input and output impedances. So there are two parameters of amplifiers. One is the input impedance, other one is output impedance. The input impedance generally will determine from the input side, whereas output impedance will obtain from the output side of the amplifiers. There will be a improvement in the input impedance and output impedance. It depends upon the feedback amplifier used. Either if it is a voltage series feedback amplifier, there will be an increase in the input impedance and there will be decrease in the output impedance. So that is very important while designing any amplifiers and all. The last property is extend the bandwidth of an amplifiers. So bandwidth means it is the difference between a upper cutoff frequency and the lower cutoff frequency, and there will be a improvement in the bandwidth, or it is a range of frequency the amplifier is operating. This is called as a bandwidth. So if I use a feedback concept in amplifiers, the bandwidth will be improved. So these are the properties of negative feedback amplifiers. Next we'll discuss advantages of feedback amplifier. So gain is stabilized. You will get a stable gain because there will be a less distortion. So gain will get a stable gain. Then second point is a significant extension of bandwidth. So bandwidth will be improved if I use a negative feedback amplifier. And very less distortion. The distortion will be reduced. There will be a chances of distortion due to interference or due to temperature variation or due to a circuit components and all. Everything will be reduced. Then there will be a reduction in the output resistance of an amplifier. The next point is a stable operating point. The operating point of a transistor or a biasing network, it will be stabilized. Then reduce noise and other interference in amplifiers. So these are the advantages of negative feedback amplifiers. The next we'll discuss about types of feedback amplifiers. Basically there are four types of feedback amplifiers. Amplifiers are there. And generally in block diagram, you are having a source, then you are having a mixer network, then basic amplifiers, then sampling network, and finally the load. And down you are having the feedback networks. And based on this mixer network and the sampling network, it is classified into four types of feedback amplifiers. The one is voltage series feedback amplifier. As I mentioned here, the sampling either voltage or current. The sampling network is voltage and the mixing is series, then we'll call it as a voltage series feedback amplifiers. If the sampling is voltage and the mixing is in terms of parallel, we call it as a voltage shunt feedback amplifiers. Then third type is current series feedback amplifiers. The fourth one, current shunt feedback amplifiers. It depends upon the mixing network and the sampling. Either you can sample voltage or current. If it is a voltage sample, then we will call it as a voltage. And here in terms of mixing network, there are two types of mixing networks. One is series mixing, other one is shunt mixing. If it is a voltage and series mixing, we'll call it the voltage series feedback. And if it is voltage and parallel mixing, we call it the voltage shunt feedback. If it is a current and series, then current series feedback amplifiers. And current and parallel, then we'll call it the current shunt feedback amplifiers. So in your syllabus, they mentioned only the voltage series feedback amplifiers. And here you have to discuss about the block diagram of voltage series feedback amplifiers. Then obtain the gain of an voltage series feedback amplifiers using feedback. Then input impedance, output impedance, then gain stability. So this is about a voltage series feedback amplifier. The figure shows the block diagram of voltage series feedback amplifiers. So here, this is your voltage source, and this is a mixing network. This is a mixing network here. We'll mix input voltage and the feedback voltage here. Now this is a basic amplifiers, and this is a sampling network. And here you'll use a series mixing. Here you'll sample voltage, and here you'll mix in terms of series. And the basic amplifier is here voltage amplifier. So it is a ratio of output voltage by input voltage. So A will be given by V0 by Vi. And this is again the feedback network. The feedback network is made up of a passive component. It is in terms of a combination of R and the passive components. And for a feedback network, the input voltage is V0, output is Vf. So here you will get voltage, let's call it as a Vf. This Zi indicates input impedance, that is without feedback, and ZIF indicates input impedance with feedback. Similarly, at the output side, you are having Z0. Z0 is called as output impedance without feedback. The Z0F is the output impedance with feedback. This is your load resistance, and here we will measure the output voltage. So this is a block diagram representation for a voltage series feedback amplifiers. Here series network, and this is voltage sampling. So the voltage is sampled at the output and fed back in series with the input. It is also known as series parallel feedback. The series parallel feedback. So now we'll obtain the gain of an amplifier with feedback. We'll obtain the equation for AF. The first we'll discuss the gain of the basic amplifier. The without feedback is given by A, that is given by V0 by Vi. So V0 is the output voltage here, and this is Vi. So V0 by Vi gives the gain of the amplifier without feedback. I'll write this equation as equation 1. Next, overall gain of the amplifier, that is given by considering this feedback network, is given by AF. AF indicates the feedback here. It is equal to V0 by Vin. And the Vin so overall gain of the amplifier is given by AF, that is given by V0 by Vin. And the Vin I write in terms of feedback voltage and this Vi. The Vin is the voltage is applied at this point, and this Vi will be written as Vin minus Vf. Next, the feedback factor. The feedback factor is denoted as beta, that is given by output by input. So output is here Vf, and input to this feedback network is V0. So that is given by Vf by V0. So I'll consider this as equation 2 and this as equation 3. Now from this I'll obtain the equation for the gain of the amplifier with feedback. So I have 3 equations now. One is A, A is equal to V0 by Vin. V0 by Vi, that is the gain of the amplifier without feedback. And the second one is AF, that is the gain of the amplifier with feedback. Then third equation is feedback factor. It is given by Vf by V0. So from equation 1, we can write V0 is equal to A into Vi. So I'll name this equation as 4. Then from equation 3, you can write Vf is equal to beta into V0. Write it as 5. And from the figure, you can observe that the input voltage that is applied to the basic amplifier is given by Vin minus Vf. So there will be a difference between the two voltages. The Vin is the source voltage and Vf is the feedback voltage. So that is equal to Vi. Now from equation 5, you can write Vin is equal to Vin and Vf is what? Beta into V0. So I'll write Vin minus beta into V0. Now I'll name this equation as 7. Now from equation 4, we know that V0 is equal to A into Vi. So V0 is equal to A into Vi. I'll substitute as Vin minus beta into V0. So I'll multiply here A into Vin minus beta into A V0. So I'll take all the output term to the left hand side and the input term to the right hand side. So V0 plus beta into A to V0 is equal to A into Vin. V0 into 1 plus beta into A is equal to A into Vin. Therefore, overall gain with feedback is given by, now that equation AF is equal to V0 by Vin. I'll take the ratio of output voltage by the input voltage, that is Vin. It is given by A divided by 1 plus beta into A. So this is the overall gain of an negative feedback amplifier. That is, for voltage series feedback amplifier, the gain will be given by AF is equal to A divided by 1 plus beta into A. From this equation, you can observe that the negative feedback reduces by a gain factor of 1 plus beta into A. And if we'll assume that beta is very much greater than 1, here the second term is very much greater than 1, then this equation I can write it as AF is equal to 1 by beta, because A divided by beta into A get cancelled, so we'll get 1 by beta. This means that the feedback gain is independent of the amplifier gain A, and any variation in magnitude of A does not appear in AF, which means AF has high gain stability. So this is one of the advantage of an feedback amplifier. So it depends upon the feedback factors. If there is any variation with respect to the feedback factor, the gain will be changed. It does not depends on the gain without feedback. So very important, this equation you should remember that AF is equal to A divided by 1 plus beta into A. So you can expect the problems also. In the problems they'll give the gain without feedback, A will be given, and you need to calculate the gain with feedback by using this equation. Or sometimes the gain with feedback will be given and you need to find out A, that is the gain without feedback, or you can calculate beta also. And even theory point of view also, we can now expect the derive the expression for a gain with feedback of voltage series feedback amplifiers. So next we'll discuss some of the parameters like input impedance, output impedance, then bandwidth, what is the changes with respect to the bandwidth and all. So input impedance, as I mentioned in the block diagram, the ZA indicates the input impedance without feedback. Then input impedances increases with feedback, and that is given by, so by using a feedback network, there is increment in the input impedance. You can observe this equation, the ZIF is equal to ZA into 1 plus beta into A. So for input impedance, 1 plus beta term is multiplied. So suppose if I'll consider ZA is 1 kilo and the signal, this will be multiplied to that, so there will be an increment in the input impedance. Generally in a voltage series feedback amplifier, the input impedance will be improved. And you have to just remember the equation here, ZIF is equal to ZA into 1 plus beta into A. So next is output impedance. let Z0 be the output impedance without feedback. That is, we will determine from the output side. Then output impedances decreases with feedback, that is given by Z0F is equal to Z0 divided by 1 plus beta into A. So output impedance will be reduced by a factor 1 plus beta into A. Because it is divided by 1 plus beta into A, so obviously if something is divided, we will get there will be reduction in the output impedance. So for a voltage series feedback amplifier, the output impedance will be reduced. So these are the two very important parameters of any amplifier circuit. And if I will employ a voltage series feedback amplifier, there will be an increase in the input impedance, and at the same time there will be decrease in the output impedance. So this is one of the advantage of the feedback amplifiers. There will be a control in the input and output impedance. Step about the gain and bandwidth of feedback amplifiers. So if I write the frequency response of any amplifiers, the frequency response means the variation of gain with respect to the frequency. So in the x-axis you can observe there is a frequency, and the y-axis I'll write it as a gain. And we'll increase the frequency. Initially the gain will be increased, and at the mid frequency the gain will get a constant, and at the high frequency again there will be reduction in the gain. So this is called as the frequency response of an amplifier. So negative feedback reduces the gain of the amplifier. As the gain bandwidth product of an amplifier is constant, the bandwidth increases with feedback. So you can observe here, usually we'll obtain the cutoff frequency. This is F1 is called as a lower cutoff frequency here, and F2 we will call it as a upper cutoff frequency. And this is the frequency response for without feedback. This is the frequency response for with feedback circuit. Now if I take the ratio difference between the F2 minus F1, that is bandwidth without feedback, will be given by F2 minus F1. And here the bandwidth with feedback will be given by F2F minus F1F. You can observe there is an extension in the bandwidth. This cutoff frequency will be determined at the 1 by root 2 of the maximum value. So in dB scale we write in terms of minus 3 dB. That is 20 log of 0.07 will get minus 3. So we'll determine at the minus 3 dB value. That frequency will call it as a cutoff frequency, the F1 and F2. So if I use the feedback, you can observe here this F2 minus F1, this is bandwidth without feedback, and F2F minus F1F is the bandwidth with feedback. And by looking at this graph only, you can observe that there will be a increase in the bandwidth. So always this bandwidth with feedback will be greater than bandwidth without feedback. So this is one of the advantage of the feedback amplifiers. By using a feedback concept, so we can improve the bandwidth. At the same time, the gain will be stabilized. So any variation with respect to the changes in the circuit components or temperature variation, all without feedback, generally the gain will not be stabilized. But if I use a feedback concept, the gain will be stabilized. And this is the A0, we'll call it as a midband gain without feedback, and A0F is the midband gain with feedback. So this is A0, and A0F is the gain, midband gain with feedback, and this is without feedback. So this is about the gain and bandwidth of the feedback amplifiers. How we will measure the gain and how we will write the bandwidth and all. Next is gain stability with the feedback. How we will check this gain stability with feedback? For that I have to use the equation for a gain with feedback. So we know that the overall gain of an amplifier with negative feedback is given by AF is equal to A divided by 1 plus beta into A. To check the gain stability, I'll differentiate this equation with respect to A on both sides. So I'll differentiate this equation with respect to A on both sides. So I'll get d by dA of AF is equal to d by dA of A divided by 1 plus beta into A. So you know that the differentiation of this, I'm differentiating with respect to A. So it will be 1 divided by 1 plus beta into A whole square. Now I'll rearrange this. I'll write it as dAF by dA. I'll write it as 1 divided by 1 plus beta into A into 1 divided by 1 plus beta into A. So I'll just write it like this. dAF by dA is equal to 1 divided by 1 plus beta into A, and I'll multiply and divide by A. So I'll multiply and divide by A for this particular equation. So that will be A divided by A. So A divided by 1 plus beta A, I'll write it as AF. And again the denominator also I'm having A. So I'll write it as 1 divided by 1 plus beta A into AF divided by A. Now I'll take this AF to the left LHS and dA to the RHS. So I can write it as dAF by AF is equal to 1 by 1 plus beta A into dA by A. So if beta A is very much greater than 1, then I can write dAF by AF is equal to 1 by beta into A dA by A. So this shows that a relative change of dA by A in the basic amplifier gain is reduced by the factor beta into A in the relative change of dAF by A in the overall gain of the feedback amplifier, thereby increasing the gain stability. So you can observe that d by dA means there is a change with respect to the gain, and this change with respect to the gain with feedback depends upon the change with respect to the gain without feedback, but it is divided by a factor of beta into A. So the gain will be stabilized. By looking at this equation, you can so that there will be a stabilized gain will get about the gain stability with feedback. So this is about the feedback amplifiers. So you have discussed about what is feedback amplifiers. Feedback amplifiers means the part of output is fed back to the input either in terms of voltage or current. And basically there are two types of feedbacks are there. One is positive feedback, other one is negative feedback. And the positive feedback concept is used in oscillator circuits, whereas negative feedback concept is used in amplifiers. Then we discussed about the properties of negative feedback amplifiers, then advantages of negative feedback amplifiers, then types of feedback amplifiers. Basically there are 4 types of feedback amplifiers are there. One is voltage series feedback amplifier, voltage shunt feedback amplifiers, current series feedback amplifier, then current shunt feedback amplifiers. So in that we discussed about voltage series feedback amplifiers, and we have derived the equation for a gain with feedback, that is we call it as AF. AF is given by A divided by 1 plus beta into A, where A is the gain without feedback and beta is the feedback factor. Then we discussed about input impedance. There will be a improvement in the input impedance and improvement in the output impedance. The output impedance will be decreased. Then we discussed about the gain and the bandwidth. You know, the bandwidth is the difference between the upper cutoff frequency and lower cutoff frequency. And if I use a feedback concept, a negative feedback concept in the amplifiers, then there will be an extension in the bandwidth. Then we checked about the gain stability with respect to the negative feedback. There is any changes with respect to the gain with feedback, there will be change with respect to the gain without feedback. So gain will be stabilized. So this is about the feedback amplifiers. Here I can expect the problems on calculation of the gain. the with feedback and without feedback. Either the gain will be given in terms of the without feedback gain will be given. You have to calculate the gain with feedback, or AF will be given and you need to calculate the A and all. So this is about the feedback amplifiers. Thank you.